Hi guys, uh, in this lecture series on design of reinforced concrete structure, last time we talked about the working stress method, which nowadays in most of the cases has become of historical importance because the people are generally using limit state method except at the places where the concrete may be exposed to water. So just to ensure no cracking, limits working stress method is so conservative that it doesn't allow any cracking. So for those no cracking condition design, the working stress method is being used. Now we would just like to see that what are the basic philosophy of limit state method. Limit states are the acceptable limits for the safety and serviceability. Mm, and so these two requirements the limit state has to fulfill, and if the safety or serviceability in any one of which is hampered, then we should consider that the structure has undergone failure. That means it may so happen that the structure is standing and it is safe, but there is too much deflection in some places. For that, maybe some operational activity, maybe the operation of the machine is getting disturbed. So we may consider then that the structure has failed for that functional purpose. Now, the most beautiful thing of this limit state method is that it has introduced the concept of probability, as we were discussing last time, that any incident in this world are of probabilistic nature. We cannot say with very certainty that, well, this incident will happen, must happen. We can't say must. So there is always a probability, even the things which is most expected, that may not occur. For example, you see, I used to tell that even if you have prepared a cup of tea and you are thinking that you are just going to take tea, and so you are sure about it that you'll have the tea, everything is made, put it in the cup, but still there can be many slips between the cup and the lips. Maybe that when you are just picking up the cup, then it has slipped out from your hand, and then everything has gone. So this this is a small probability of failure. So in the same way, everything in this world is probabilistic. So the aim of this design is to achieve some acceptable probability. It is not telling that to achieve safety directly. That means it will be safe in all situations. So, so what it is telling is that to achieve acceptable probabilities, that the structure will not become unfit for use for which it is built. That is, and this state, that means just before the failure, the state is called limit state, and the objective is that the limit state will not be reached. Now, if you look at the stress strain diagram, then you will see, of course, the strain diagram depends on the geometrical aspect. That means how two planes are rotating with respect to each other because of the bending, and that's why the strain diagram will be linear uh, as we are seeing in the figure. But limit state allow the maximum strain in the extreme fiber uh, to exceed the yield value and to exceed up to certain point, such that these fibers become, so not only the fiber at the edge, but also uh, below that, the fibers whatever is there, they also undergo yielding, and that's why you see almost up to this, the fullest load carrying capacity of the fibers are used. And then it is because of allowing a stipulated amount of strain even beyond the plastic strain. So as a result of that, the stress block, and then beyond this region, uh, the strain is allowed in such a way that the stress becomes reducing, maintaining a maintaining approximately a parabolic form. While at the bottom of the neutral axis, all of you know that the bottom of the neutral axis will be subjected to tension when we are talking about bending. Then that neutral axis, so the area under that neutral axis will be under tension, and therefore it will be a strain in the strain diagram, though it is linear, but in the stress diagram, these concrete cannot take any tension, so it will take the zero value, and only when it will encounter the steel, then the steel will try to take the entire amount of tension what is supposed to generate in this region. So the stress diagram become like this. The upper part is uh, parabolic, while the lower part is having some concentrated uh, loading, uh, tensile loading, which is being carried by steel. So this method is based on a more practical stress strain curve of steel and concrete, and both even we allow some amount of inelastic stretching in the steel also, because we would also like to utilize the ductile behavior of the steel uh, to some extent, and that basically gives us economy, because a situation come when the giant structure started coming up, uh, of course not that giant what we are having nowadays, but even as compared to the time what I'm talking about, there a big structure means a say 5-story structure or 10-story structure that was called sufficiently big structure, and therefore there we we thought that, well, to reduce this cost for those giant structures, the actual stress strain curve should be used, so that the load carrying capacity of the material can be more appropriately and more optimally utilized. Now, the next question is that how many such limit states may be there? You see, there are two limit states primarily considered. The first one and most concerning one is the limit state of collapse. That means the building should be allowed to go up to that state only, beyond which it will undergo a complete collapse. That will cannot happen. Then second thing is the limit state of serviceability. The example I was giving, that maybe a building where a very important and heavy machine is installed, and so something happens in that part of the building, because of that the machine stops operating, so then it will say that the limit state of serviceability is not being maintained. So uh, so these are the two states which are both parallelly taken care of in limit state method, and you can understand that as in as against the working stress method, where we were only considering the safety of the member, that they should not undergo any cracking or any failure. Here, parallelly, we are also considering the serviceability, because whenever we are making a building, we want some service from that building. So these are the two issues which are kept together into the consideration while limit state design. So the limit state of collapse primarily taken care of the stress generated due to flexural effect, shear effect, and then won't slip due to torsion or due to compression. While the limit state of serviceability is primarily hampered due to deflection, cracking, or uh, vibration, which can be which is large enough so that it can be failed, or even the machine or anything what was sitting on the structure that is disturbed. The functionality of those are disturbed. So So limit state always use the concept of characteristic strength. It doesn't say that, well, the concrete is having that much of strength. No, because uh, maybe that some part of the concrete may have that much of strength. Some of the concrete part may have more than that. Some of the concrete part have less than that, because it is also a probabilistic phenomenon. Whenever we have uh, designed for a particular strength, then we are not sure that whether the all portion will have uniformly that much amount of strength, because we are mixing cement, sand, and coarse aggregates and water, and the mixing may not be absolutely homogeneous mixing. So they have coined a term called characteristic strength, which means that value of the strength of the material below which not more than 5% of the test results are expected to fail. It means that if I test 100 cube, if I uh, design for a particular strength, and then from that concrete, if we make 100 cubes, then at least the I mean, not more than 95 cubes will have the strength which is shown here, the strength lesser than FCK. Only we can allow 5%, which is being shown here by this small triangular looking part, there, that this should be this much amount of this many number of cubes, which is denoted by this, can go up to can have a value lower than the uh, our target strength. So the actual, and we will consider this FCK as the strength of that particular concrete or material, because uh, we want safety in general. So, and we accept that all the incidents are probabilistic. Therefore, only we will leave 5% probability uh, such that the material strength can go below the stipulated value. And that's why if we like to design for 20 Newton per millimeter strength, then my FCK is 20 Newton per millimeter, then we have to target a much higher value, so that that becomes the mean strength, and more precisely it is speaking as target mean strength. And similarly for the load, but it's from the opposite side. That means we will consider that as the characteristic load, which is having only 5% of probability to exceed. So it is called characteristic load. So the beauty lies in the fact that the concept of probability is is already hidden in this approach, and therefore when we are trying to uh, arrive at an optimal design, there we have to be very sure before reducing the section, which was going in the traditional method. We have to be doubly sure that we are not violating the safety requirement, and in order to do that, to be more careful, these probabilistic concepts are included in this study, in this limit state method. And accordingly, if you go to the code, then you see that there are various design values of the material. That means even if the characteristic strength you obtain depending on the type of material you use, we use a partial safety factor. It is not called factor of safety, it is partial, because for one particular type of material it is valid. For example, if we consider concrete, then while making the concrete, even if we know the proportion, but when the masons and other people are working, then how much control we are having on them. Maybe in some places, while making the mix, they have put more water, so the safety is hampered. That is why a larger factor of partial safety factor, 1.5, is used for concrete. Gamma m denotes the partial safety factor. While when we are talking about the steel, then steel is being made in a factory in an automated process, and then therefore there is a very less possibility that it will not meet the requirement of the attributed strength or predicted strength. So there we'll have lesser factor of safety. So this clearly proves that this this approach is having a much more scientific consideration, so that where depending on the material, depending on the system, depending on the functional requirement, we are uh, incorporating the adequate factor in the process, and we are designing the trying to design the structure. So more we will discuss, this philosophy will become more clear to you. So that's all for today. We'll continue the same thing in the next class.